All right. So we will continue what we have stopped from yesterday. Okay. So today we will continue for bipolar junction transistor BJT, which is part 2. Yeah. So BJT is actually we have two analysis, which is AC analysis and DC analysis. So for this week, okay, we're going to focus for DC analysis. Actually, DC analysis will cover until BJT, BJT circuit analysis. But I think BJT circuit analysis I will separate to next week because we need lots of explanation, and I think we need extra time. So in a 2 hours is not enough now. Okay, right. So for today class, okay, we will continue on the parameters and characteristic of BJT. Okay, right. Okay, and then we will. Okay, and then we will continue with the basic DC model of a BJT, and then we will interpret the collector characteristic curves, which is the active region, saturation, and also the cutoff. Okay, we will see each characteristic. What is the types of diodes are going to be. Okay, either it is a forward or it is a reverse. Okay, so for each region. Okay, and then we will discuss and we will determine the DC operating point. Okay, we're going to look into detail what is the DC operating point, okay, of a linear amplifier for a Q point. Okay, we will see the Q point. What is a Q point of the graph from the IV curve? Yeah, IV curve. All right. So a little bit recap from yesterday's class. Yeah. So this is the this is the two types of BJT. Okay, as I mentioned before, BJT. Okay, BJT have two types, which is PNP and also NPN. Right. So to determine or to distinguish between these two types of BJT, you can look at the direction of the currents at the emitter point. Okay, so if it is goes into base and collector, it is a PNP type. Yeah, for this one, this is the PNP type, since that the current from emitter is entering the base and also collector. But if the current from base and collector entering emitter, so it is the NPN type. Okay, so if you want to differentiate between or analyze what type of transistor is that, so please look at the direction of the currents at the emitter. Okay, so what each function of emitter, base and collector. Okay, also you have to know, okay, for emitter, it sends the carriers into the base region and then into the collector. For the base, act as control region. Okay, so base is as a control region. Okay, so the carriers flow depending on the biased voltage, how much bias voltage that you applied at the base. Yeah, and also collector, it collects the carrier. Okay, as it aims, okay, it collects the carriers. And also you should know beta beta DC and also alpha DC, okay, and how to calculate them. Yeah, this one I think is very important because you will use this for the calculation for the circuit analysis. All right. Or this also known as IC equals to beta DC IB, right? Okay, so this is the example of current flow in NPN type. Yeah, so the external voltage from the VBB, yeah, from the VBB at the base part. Okay, the currents will flow here. Okay, so since that this is NP and N, so at this junction, this is a forward. Okay, this is forward. Why it is forward? Because this is at the same polarity. This external source meet the same polarity, which is plus for the NPN. Okay, so this is forward. Okay, and then this is reverse. Yeah, this is reverse because it is different polarity. Positive meet with negative. Okay, so the currents flow from collector and base will enter the emitter. Okay, and then this is the PNP type. Yeah, PNP type. For your knowledge, yeah, this is not always forward. This will not always reverse. Okay, it depends on the voltage value. Okay, at the VCC and also at VBB. Okay, so for this we will just mention this as a forward lah. Okay, because we don't know how much value. Okay, let's say that if VCC value is higher compared to VBB, so at here, yeah, at this junction, it will be reverse bias. Okay, so in this case, we assume that VBB is higher compared to VCC. All right. So for here, for here, okay, for the PNP junction, yeah, for PNP transistor type, the emitter current, okay, will flow from emitter, and some of the currents will flow to the base, and most of the current will flow to the collector. Okay, why only some of the current will flow to the base? Because if you look at the junction, the depletion region, yeah, the depletion region usually, yeah, in the middle, at the middle here, the depletion region is very narrow. It is not wide. So since that the depletion region is narrow, okay, so since that the depletion region is narrow, so only few, okay, only some of currents will flow to the base, and most of the currents will flow to the collector. Okay, all right. So this is just a recap or a revision from yesterday's class. Yeah. Okay, so for yesterday we stopped at this graph, right? The collector characteristics curves. Okay, so what this graph shows, right? So this graph shows, yeah, the when we change VCE, okay, when there is a changes of VCE, okay, VCE voltage at VCE collector emitter, what will happen to the current of at the collector? So this is going to be the graph of current at the collector when when you change the value of voltage at the collector emitter here, VCE, right? So at first stage, okay, at first stage, when you increase the VCE value, okay, when VCE value is increasing, okay, the currents for collector also will increase rapidly. Okay, you can see that the gradient here is very sharp. Yeah, the gradient here. But at some points here, the value of currents will start to saturate. Okay, will start to saturate. It means that it's very small changes of the collector currents. So we call that a saturation region. So after the VCE surpass, okay, exceed the 0.7, which is potential drop for the transistor here, 0.7 volts. Okay, you can see when we increase the VCE, okay, the currents at the collector will also increase, but as not aggressive as at the AB. Okay, it will increase gradually, slowly like this. Yeah, the slope is quite it's not so gradient compared to the AB. Okay, and then when all right, and then when the VCE at the maximum voltage value, okay, VCE at the maximum voltage value, right. So when VCE at the maximum voltage value, same with diode or rectifier, okay, the transistor will be at the breakdown region. Okay, will be at the breakdown region. So it means that this transistor will off, yeah, will not work anymore. Okay, so usually, yeah, okay, so VCE, okay, VCE, okay, VCE usually, okay, okay, VCE is depending on the currents. Okay, the value of voltage VCE is depending on the value of currents that flow at the base of the transistor. Okay, so when you change, okay, so this, since that is, you can see here that the voltage source here is a variable. It means that the value can be changed. Yeah, it's variable voltage source. So when you change the value of voltage at the base, yeah, at the base here, okay, the currents also will change, right? So it's significant, yeah, because V equals to IR. So when you increase the voltage, okay, since that the resistor is same value, so I also will be increased, right? So and according to the beta DC formula, okay, which I had mentioned yesterday, so IC is equals to beta DC and IB. So beta DC is given usually. The value is always same. Okay, value is always same. IT. Okay, so since that the value is always same, so when IB is increased, IC also increase. So we're going to look into detail what are the relation between these two. Okay, so we look here, yeah. So here, this graph is much details about at here region. Okay, when we increase TIB. Okay, so when IB, first of all, when IB is 0, okay, the area under this graph will be, it is called as cut-off region. What does that mean of cut-off region? Cut-off region means that the transistor will not work. Okay, same as breakdown, the transistor will not work. It is on an off state. Yeah. So at the when the at the low, how to say, at the area of down part here. So this is what we call as cut-off region for this transistor. Okay, so when IB is 0, this is the value, yeah, of IC. So when you gradually increase the value of IB1, okay, IB, okay, let's say this is the value for IB1, IB2, IB3, IB4, IB5, IB6, you can see that the value for IC also increasing, okay, okay, and the value of IC also increasing, and the graph from point A to point B will be the slope, yeah, the gradient will be sharp. Okay, when you increase the IB, okay, the value of IB. So it means that when the value of IB is too high, so it will makes the more current flow rapidly. Okay, gradually changes of the currents at the collector part. Okay, so this is it shows, yeah, it shows that this formula, okay, this formula is relatable with this graph. Okay, it's same with this graph. Okay, now we're gonna look into details. Okay, what are the the region for each graph just now. Okay, so sorry, forgot to mention at BC. Okay, at BC, at point B and C here, we call this region, it is an active region. It means that at this region, the transistor will work, okay, will on. Okay, so active region, it can be divided into two parts, yeah. Either it is a reverse active region, okay, or it is active, forward active region, okay. So okay, if you still remember, I do mention yesterday, since that diode, they have two types of bias, right, for diode. diode, sorry, diode, okay, diode. Two type of bias, which is forward bias and reverse bias. But for transistor, we have four types of bias. So these are the types, yeah. So it is a reverse active, saturation, forward active, and cut off. So how you want from the graph, yeah, how you want to, not from the graph, from the graph and circuit, okay, from the graph and circuit, how you want to identify either the transistor is in what region, okay. So this will help you to identify, okay, this will help you to identify that the transistor in what region, okay, in what state on it. Okay, so VC is referring to the V at the collector, okay. VB is referring into voltage at the base. Okay, and VE refer to the voltage at the emitter. Okay, so when VC, okay, when VC smaller than VB and value of VB is smaller than VE, so it means that voltage at the emitter is larger compared to base and collector. So it means that the transistor is in the reverse active region. Okay, reverse active region. Okay, so when VE, which is voltage of at the emitter, is smaller compared to voltage at the base, yeah. So it means that the current flow here is larger compared to here. So, and also VC, okay, voltage of at the collector is smaller compared to voltage at the base. So it means that the transistor is in a saturation region. Okay, so at the saturation region, you can see that the value at the voltage, voltage value at the base, yeah, at the base part, okay, at the base part is larger compared to C and E, collector and emitter. But for reverse active, the value for voltage is larger at emitter compared to base and collector. Okay. So for cut-off region, okay, so value of cut-off region, it is either VE, okay, voltage at emitter is larger compared to voltage at the base, or, okay, or voltage at the collector is bigger compared to voltage at the base. So it means that at this two region, yeah, at this two at this two junction, the value of voltage is bigger compared to this value at the base. So it means that the the transistor, it is in a cut-off mode. Yeah, cut-off mode. It means that the transistor is not operated. Okay, it is in a off state. Okay. Next, for you to determine either the transistor is in a forward active or not, okay, so you need to identify that the voltage value at the collector here is bigger compared to voltage value at the base and voltage value at the emitter. Okay, so it means that the value of voltage at the collector is bigger and larger compared to base and also emitter. All right, so so it means that the diode is in a forward active region. Okay, so what are the function of this? Yeah, what are the function of by knowing what are the operations of the transistor? Okay, so by knowing this, either the transistor it is in a saturation or in a cut-off operation, it is applicable. Yeah? It can be applied. Okay, the transistor can be applied in a digital circuit like switching. Okay, this two state is very important. Yeah, it's very important to identify the state of the transistor in order for you to use this transistor for a switching. Okay, so switching, either you want to switch the circuits, yeah, on or off, okay, by time. All right. So active region are important for amplifier application. Okay, so this active region, yeah, is very important for amplifier applications. So you can see that for reverse active, okay, when you want to use reverse active, when the voltage at the emitter is larger compared these two. For forward, voltage at the collector is bigger compared to base and emitter. So it means that you are amplifying the currents or the voltage. Yeah. So active region, both reverse and forward, it can be used in amplifier application. For saturation and cut off, you can use this transistor for a switching. For a switching application. Okay, so it is very important for you to know the Allahu Akbar. So it is very important for you to know the application of transistor. Okay, in each stage. In each state, yeah, all right, because sometimes in paper 1 usually in your test they will ask you, yeah, at what state the transistor can be used for switching, at what state the transistor can be used as amplifier application, or what are the function of transistor. So the function of transistor, it can be used for switching and amplifier. So switching when it is in a state saturation and cut off operations, and amplifier when it is in a active region operations. Okay. Right. So for this tips or for this apa ni namanya, for these rules, okay, it is applicable for NPN and also PNP transistor. Okay, so it is not only this type of transistor, it can be applicable for both NPN also PNP. All right. So next, let's look at the example 1. Okay, example 1. Sketch an ideal family of collector curves for the circuit in following figure for IB, where IB value is 5 microamps to 25 microamps. Yeah, from 5 to 25 microamps, since that the external voltage source is variable. So it means that the value of currents also is variable. So it's variables from 5 microamps to 25 microamps in 5 microamps increments. Yeah? So assume that beta DC is equals to 100 and the VCE does not exceed breakdown. Okay, so it means that the VCE here is not exceed the breakdowns. Okay, so since that we know this formula, so when you know this formula, you can always find the value of IC, okay, collector currents, okay, currents at the collector parts by using this, the value of beta DC, right? So you just plot for each, since that this is 5 microamps increment, so it means that start with 5 microamps and then 10 microamps, 15 microamps, 20 microamps, 25 microamps, and then for each value for IC, you can use this formula and then you can plot, and you can plot here. So make sure, okay, for you to plot the graph, make sure that you take note, the value of potential drops, for the transistor here. So usually the value is 0.7 volts. Okay, so after 0.7 volts, the graph will be saturated. The graph will be linear like this. Okay, the graph will be linear like this. Okay, so yeah, so this is another point here for you to plot the graph. Okay, for you to plot the graph. Okay, next, I think this is very easy for you. Okay, let's look into detail what is cut-off regions. What is cut-off region? So cut-off region happen when IB, the value at the current at the base, is equals to 0. Okay, when IB is equals to 0, the transistor is in cut-off region. Okay, why? Because the value of currents, okay, the value of current the value of, sorry, not the value of currents, the value of voltage of VCE here, since that there is no external current or external, since that IB is 0, so it means that the VBB is also 0, right? So since that there is no currents flow here, okay, the value, the voltage, okay, the voltage of VCE here is equal or approximately VCC. It will not be equal to VCC because there is RC here. So there will be a few of potential drops here to RC. So but the value will be not so far different with VCE. So we can say that equal approximately, approximately to VCC. Okay. All right, now, but there is still ICO will flow. Okay, there was still ICO flow here in this transistor, okay, in this resistor, mainly because of the thermally produced carriers, and the value is very, very small and it can be neglected. You don't have to bother about the value of ICO here because the value of currents here is very, very small, yeah. And so VCE approximately, okay, or we can say equal as VCC, all right? So in this condition, neither the base emitter nor the base collector junction are forward biased, okay? So since that there is no current flow, both of them, yeah, base emitter, BE, or base collector, BC here, none of them are in a forward bias mode, right? Since that there is no current flow at all, right? So next, let's look at the saturation. What happened into saturation, yeah, at the saturation region? So when the base emitter junction becomes forward bias, so when the base emitter junction becomes forward bias, so it means that there is a current flow from here. So it means that the VBB value now is no longer 0. Okay, so some currents flow here. Okay, so when the base emitter junction becomes forward bias, the base current is increased. So it means that the currents here is increasing, yeah, and the collector also increases. So since that from this formula, yeah, when the IB increase, okay, beta DC IB equals to IC, right? So when IB is increasing, okay, IC also increases, yeah. And since that IC is increases, VCE will be decreases. Okay, so this is pertentangan ataupun different the other way around with IC. Yeah? So VCE is decreases. Why? Because the value of VCE equals to, you have to calculate, okay, you have to calculate the VCC, the VCC should minus with the potential drop from the resistor here. So the value from VCC will no longer all goes to here. Okay, since that the currents here flowing, okay, and it is increasing, so it means that VC here, yeah, the voltage, the potential drop at the resistance here also are increasing based on the value of the currents, IC currents. So VCE, since that this value will keep increasing and increasing, right? Since IC is increasing, so the value of V equals to IR, right? So when I is increasing, R is it is constant, so V also will increase, right? So when this value is increasing, it will become VCC minus something bigger, right? So VCE will be decreasing, okay? So the potential drop at collector resistor can be calculated using this value, all right? So this, it is actually VCE equals to VCC minus VC, where VC is the potential drop at here, okay? Where VC is equals to IC times with RC, okay? Where to get this IC? IC is from the beta DC IB, okay? All right, so when VCE reaches saturation, okay, So VCE at some point it will reach saturation, okay, saturated value. The base collector junction becomes forward bias. Okay, so the base collector B and C here at this point here becomes forward bias, and IC cannot further increase even is when IB is increased. Okay, so IB, okay, IB, even though it is increasing, IC will be limited with the value of saturation. Okay, it will reach a saturation value. Okay, so this at this junction here, there is a saturation value that will control the currents, that will limit the currents. Okay, it will not keep increasing the currents that flow to the collector. Okay, it will be limited by the saturation value. Okay, so when it reach this saturation value, the junction for the base and collector here will become forward bias. So it means that since that it is saturated, no more increasing, the value will not change anymore. So IC will become constant. IC will become ET. Okay, it will become constant and it cannot further increase even if IB is increasing. Okay, so at the point of saturation, the relation IC equals beta DC IB is no more valid. You cannot use anymore. Okay, so to use this formula, okay, there is a rules. The rules is to make sure that the value of VCE is not reach the saturation yet. Okay, not reach the saturation. Okay, how to know either the VCE, what is the value of saturation for VCE? Usually it will be given. Okay, it will mention to you. Okay, so that you will know the value of saturation value. Okay, so let's look BJT operating region. Okay, so this table is summarizing the BJT operating region, okay, for you to identify what will happen when it is cut off, saturation, active linear, and breakdown. Okay, so active linear, it's cover both lah, for reverse and also for forward. Okay, so when cut off region, the value of IB is very small. Okay, so this is for this row. Okay, for this row, it is either IB or VCE characteristics. Yeah, be careful. For this row, it is either the junction for BC, which is base collector, and also base emitter. Okay. Okay, so for cut off, IB is very small. The junction for base collector is reverse, and also base emitter, both of them is in a reverse mode. Okay, and it makes the transistor open switch. Open switch means there is no current flow. No current flow. The transistor is off. Okay, transistor is off mode. All right. So for the saturation region, at the saturation region, the value of VCE, okay, value of this is base, this is C, and this is E. Okay, and then this is will go here, right? This will go here. Okay, so the VCE, CE here, VCE is usually here, yeah? So VCE, the value is very small, okay? And both the BC and BE, BC and BE part here, okay. VC and BE part here, both will be forward junction, forward bias, sorry. Both of them are going to be forward bias. So it means that now the switch is closed, the transistor is on, and currents will flow. Okay, currents will flow. At the active linear, okay, at the active linear, right, VCE is in a moderate value. Okay, it will not exceed the saturation value. It is in a moderate value. The BC junction, be careful here, yeah? This is in the order. BC junction is in a reverse. BC junction is in a reverse bias and BE junction in a forward bias. Okay, so it makes at this state, yeah, at this region, the transistor will work as a linear amplifier. Okay, it will work as linear amplifier. And for the breakdown, at the breakdown region, it means that the VCEs is very, very large. Okay, it exceeds the value of saturation value. Okay, the value from the IB is very, very large. Okay, so it's beyond limits. Okay, both the BC and BE will be beyond limits, and it will make the transistor overload. Okay, usually at this state, the transistor will break. Okay, will break and it is off. Okay, it is off. Okay, so this is the summarize of all those, yeah, all those region, yeah, that you need to know. Okay, be careful for this, yeah. This is in order. This is BC junction and this is BE junction. This is BC junction and this is BE junction. This is BC junction and this is BE junction. Okay, jangan tertukar lah. Don't confuse with this, yeah. Especially, I think no problem with cut off and saturation and breakdown, but for active linear, yeah, BC is in a reverse and BE is in a forward. Okay. Okay, next, let's look for the BJT behavior, current voltage characteristic. Okay, so this is yesterday's from yesterday's slide, right? We have learned current voltage curve, yeah? IV curve, also known as IV curve, in diode and also in rectifier. It will represent the current, the relation between current and voltage, yeah, in a graph, in one graph. Okay, in one graph. So we, yeah. So, and for the BJT, okay, BJT, current voltage characteristic can represent two, input characteristic or output characteristic. For input characteristic, the relation between the graph is between input current and input voltage. Okay, input current and also input voltage. Okay, and the voltage of for different values of output voltage. Okay, so it for the relation between the input current and input voltage will give you different value for output voltage. So this is the input characteristic of graph. Okay, and also there's another graph that will represent the output characteristic. So the output characteristic will represent is a relation between the output current and also output voltage, and from this graph you will know the different values of input current. So when the graph given to you, please identify either it is input characteristics or output characteristics. Okay, we're gonna see what's the difference between I will give you example for input characteristic and output characteristic graph. So this is the input characteristic graph. Okay, where the information given inside this inside this graph is the value of voltage at the base emitter. Okay, base emitter voltage. Okay, just now, right? The graph will be, I'm not sure it is. It will be like this, right? Okay. Okay, so this is the voltage value. Apa ni? Alamak, salah pula. Okay, so this is the VBB, right? So VBE is here, yeah, the value of VBE here. This is the emitter, this is base, and this is collector. Okay, so the information of the x-axis is voltage at the base emitter, and also the y-axis. Okay, this is the y-axis. The information given for y-axis is base current. Okay, the base current at base. So this is the input current. So input voltage and input current, it will gives you the information. You will get information for output voltage. Okay, So the graph that you will plot will be output voltage. Okay, so this means that this graph, it is an input characteristic graph. So the characteristic resembles a family of forward bias diode curves. So IB increases as VCE decreases. Okay, so you can see when IB increasing, okay, the voltage for at the collector and emitter is decreasing for a fixed value of VBE. Okay. Next, ada yang baru join je. Next, let's look to the output characteristic. Okay, output characteristic. Okay, usually in your test or in your exam, yeah, output characteristic is much more famous. Yeah, please focus more on output characteristic. Okay, because from the output characteristic there is a DC load line. Okay, I'm gonna explain that later. Okay, so but this is the output characteristic graph. Okay, so the output characteristic graph at the at the x-axis. Okay, the information is the output voltage, okay, the VCE voltage, yeah, VCE voltage, and the y-axis will give you information of output current, which is the IC current, okay, IC currents. All right. Usually for this output characteristic graph, there will be much more information that you will get, okay, that will give to you. Okay, for example, there is a Q point here at the middle of the graph. There is a Q point. And also, there is a DC load line, okay, where from the DC load line, you can see when the DC load line cross the y-axis, okay, intersect with y-axis, this point or this reading, okay, this value is the value for saturation. Okay, this is the saturation value for the transistor. Okay, when the DC load line intersect or cross the x-axis. Yeah, usually this is x-axis because this is 0 and this is also 0. So it is moved a little bit further above to so that you will recognize this. So this is actually 0 reading. So it is supposed to be on here. Okay, so this is just for you to identify or to let you know, oh, this is the cutoff region. Okay, but if you look at the memory here, so this is a 0 for the y-axis, so this is a 0 for the x-axis, so it should be, this line should be on this line, but it will be confusing. You cannot see the cutoff region, so it is slightly moved a little bit above so that you can see the cutoff region. Okay, so just for your you to easily identify the cutoff region. Okay, so but when the cutoff, when the DC load line, okay, when the DC load line cut off with the x-axis, yeah, it is a cutoff region. Okay, at this point, at this reading, it is a cutoff value, the value for cutoff. Okay, so and also at the middle of the DC load line, there is a Q point. Okay, where Q point we're gonna I will explain later on. Yeah, we'll give you Q point, which is a very important point or value for the transistor. So you can see here, yeah, for the output characteristic, usually it will give you a lot more information. Okay, where you can also see the active region here. Here is the active region here. Here is the active region for the transistor. Here is the saturation region. Okay. Here is the saturation region for the transistor. Here is the saturation value, and also here is the cutoff value. Okay, so at the y-axis, yeah, when VC is equal to 0. Okay, when VC is equals to 0, the value of IC is equals to, so VCE is equals to 0. So you can see that VCE now is equals to VCC, right? So VCC divide with RL, you will get the value of IC. So that is the value for saturation. Okay, that is the value for saturation value. Okay, which is IC equals to VCC divide with the resistance load. Okay, RL. Okay, RL is load that connected to the collector. Okay, usually load that connected to the collector. So we call it is known as RL usually. Okay, so and then for you to identify the when IC the cutoff region, yeah, when IC is equals to 0, okay, VCE is equals to VCC. Okay, so this is the formula that you need to know. Yeah. And at the Q point here, VCE is equals to half VCC. Okay, Q point is the middle point or the center of the of the of the graph. Yeah, so VCE is equals usually, yeah, is equals to half VCC. Okay, so this is for you to imagine or for you to understand well what is cutoff region, what is linear region, what is the saturation region. So try to assume or try to imagine that the flow of the current transistor is just like a tap of water like this, a water tap like this. Yeah. So when you open the toggle, okay, when you open when you off the toggle, yeah, it is going to be in a cut-off region. So it means that there is no current flow, and this is actually the base part. Okay, this is actually the base part, and this is actually the this is going to be a collector and emitter, right? But when the base is 0, mean off, so it means that there's no current flow inside the transistor, and it is in a cut-off region. Okay, then when the base is on, okay, when the base is on, it means that the current start to flow. Okay, so the current start to flow, so it means that the transistor is on mode. Okay, and current will start to flow, and base will control the flowing of currents. Yeah, and at the saturation region, okay, at the saturation region, imagine that you are opening the pipe full. Okay, you want lots of water to come out, but at some time, at some point, okay, you when you turn on the tap, yeah, tap water to the maximum, there is a one point that you cannot no longer open the no longer turn the tap water. So it means that you have maximum, you have turned the toggle to the maximum point, to the maximum to the maximum. So it means that no more there will be maximum water will flow, and no more water can flow anymore on from the pipe, right? So same with the transistor. Yeah, when you when the base, yeah, when the base flow too much, yeah, when the base flow too much, it will be in a saturation region. So the currents flow inside the transistor will be maximum. Okay, will be maximum as possible, and on this saturation region, it will make the transistor fully on. Okay, fully on. You are fully turning on the transistor, so the currents at this point, yeah, is fully turned on or fully flow inside the circuits. Yeah. Okay. Up until this point, any questions? Up until here is okay, still okay, right? Okay. So if it's still okay, we're going to proceed. Okay. So next, so this is each region comparison. Okay, comparison for each region. So for the active region, okay, for active region, the BE junction both are in the forward bias. Okay, the base and the emitter junction both in a forward bias. But for the collector and the base junction will be reverse bias. Okay. When I say like this, it's better for to draw, right? So, okay. So this is the base. So this is collector. This is emitter. So base here, base emitter junction is in a forward bias, but collector and base junction will be reverse bias. Okay, and it can be employed to use as voltage and current amplification. Okay, so for active region, it can be used for amplification. All right. For saturation, okay, for saturation, both base emitter, okay, base emitter and also current emitter. Okay, be careful, yeah. Not current, sorry, not collector base or base collector. No, collector emitter. Okay, try draw here. So this is the collector, this is the emitter, this is the base, and BE, so base emitter will be in a forward bias, okay, forward bias, and also CE here, okay, CE here, collector emitter here is also in a forward bias, okay, both of them will be in a forward bias. And then IB and IC, okay, currents that flow from IB and also IC are too big, okay, too big because it is in a saturation here, fully open the tap water, okay, it is too big, but VCE will be very small because when IC equals to beta DC IB, okay, so because when the IB is flowed too many, IC is increasing, so the potential drop at the resistor IC also will be bigger or larger. So VCE, since that the VCE is equals to VCC minus to VC, yeah, VC, so it makes the VCE voltage value becomes very small, and it is this saturation region is suitable to use as logic switch, okay, logic switch. And then so logic switch, you know, yeah, I think you know this logic switch, or on and like that, yeah, or and there's one more I don't remember, or and those things, yeah. And then cut off region, okay, cut off region, the base emitter and also the collector emitter, okay, junction both are in a reverse bias, okay, this junction both are in a reverse bias, okay, so the value of IB is very small than microamps, okay, value that currents that flow inside the base at the base is very small, but IC is not zero, okay, but the value of IC is not zero, as I mentioned just now. ICEO still flowing, but the value is very small too, okay. Avoid this regional for undistorted signal, okay, so avoid this signal, avoid this region for undistorted signal. Usually at this cutoff region here, the signal will be distort, okay, the signal will be distort, okay, the signal that pass through here we're going to be distorted, so usually we're going to avoid this region, okay, to avoid the distortion signal. And then at this region it is suitable for logic switch too, okay, logic switch too. And usually at the cutoff region the switch going to be off, right? So this is the comparison of the for these three regions, okay. And I will say that this is very important, yeah, this is very important, and please please memorize this, yeah, and understand well this. Okay, now let's look at the example too. Okay, determine whether or not the transistor in the following figure is in saturation or not. Okay, now you have to identify either the transistor now is in a saturation region or not. So assume that VCE saturation, okay, the value of VCE saturation is 0.2 volts. So it means that if the value of the transistor, okay, if the value of the currents here is bigger, is larger, yeah, than 0.2, so it will meet the saturation rate, saturation, okay, this transistor will be in a saturation mode. So first of all, what you have to do is you have to determine the current saturation, the value of current at this saturation point, for the saturation point. So IC saturation is equals to value for VCC. Okay, VCC minus VCE. VCE is here, right? VCE, value of voltage at the collector emitter saturation, and then divide with the value of RC here. Okay, so 10 minus 0.2, okay, you will get 9.8 milliamps. And then C, if IB is large enough to produce IC or not. Okay, now how to determine if IC is large enough to produce IC or not? So first you have to calculate the value of currents that flow at the base here. So IB is VBB minus the potential drop for here. Yeah, please always remember that there is always a potential drops here. Okay, 0.7. So VBB minus 0.7 potential drop, and then divide with the value of the resistor here. You will get the value of the currents that flow at the base of the transistor is 0.23 milliampere. Yeah, 0.23 milliamps. So now, okay, 0.23, okay, 0.23 times with the beta DC is given to you, yeah? Beta DC is given to you. Sorry, this is equals, yeah? 50 times value of IB, which is 0.23 milliamps, you will get 11.5 milliampere. So you can see that the voltage value here is larger than the value of currents for IC at the saturation, which is 9.8 milliamps here. So it means that since that the value of IC is greater than IC saturation, so the transistor now is in a saturated mode. Okay, so it means that the transistor now is in the saturated mode, and collector current value of 11.5 milliamps will never reach. Okay, so the currents that will flow here will only be 9.8 milliamps, although in calculation it's supposed to be 11.5, but since that it's already reached the saturation value, okay, saturation value, so the maximum current, so it means that only the maximum current that will flow inside the collector. So IC saturated, okay, currents saturated at the collector part here is also, okay, is also represent the maximum current that can flow inside this transistor at the collector part. Okay, so IC saturated is also, represent or can be said, yeah, can be said as maximum current at the collector. Okay, maximum current at the collector that will flow when the IB is too large. Okay, when IB is the value of IB is larger. Okay, so by increasing the IB, now even if you increase again the value of IB, okay, it will not increase anymore the value of current that flow inside the collector, because the transistor now reach at the saturation's value. Okay, reach the saturation's value, right? So that's why, if you can see here, that's why usually, VBB, the external voltage source at VBB, usually it is in a variable voltage source. Okay, because you want to adjust, you want to adjust the value of voltage to adjust the value of currents to flow inside the base of the transistor here. Okay. Okay, now let's look. I think it's clear for the calculation just now. Okay, now let's look at what is point Q. Point Q, if you still remember inside the output characteristic of graph just now, there is a Q point. So what is Q point actually? Okay, here, right? What is Q point? So Q point, okay, this is for DC operating point. Yeah, please remember that all of this, yeah, all the formula, all the regions that I mentioned just now, it is applicable for DC. Okay, DC. So for the Q point here. What is for Q point? For the DC operating point, yeah, when BJT, when the bipolar junction transistor have only DC input, okay, have only DC input, it will have specific value of IC and VCE. Okay, so DC input means that the input of the transistor for at the base just now is no longer variable. Yeah, it is a DC input, so it means that it is a specific value of voltage applied to the base. Yeah, so when BJT only have DC input, it will have specific. Yeah, it will give you a specific of IC and VCE voltage. Okay, since that only 1 volt is applied to the base, so it will produce specific base current. So from the specific base current will give you specific value of IC and also VCE. So it corresponds on the specific point on the DC load line. Okay, it will correspond on the specific point on the DC load line, since that IC and VCE now is specific. So the point Q is also specific. Okay. Okay, so usually Q point here. Q point is placed at the center of DC load line. Okay, at the center of DC load line, in the middle of the DC load line. Yeah, it is a point on the collector characteristic curve, which is IC VCE, or the output characteristic. Yeah, collector characteristic or output characteristic curve with constant IB. Okay, with the value of IB now is constant. Okay. All right. So I think this is how this is what the meaning of Q point. So how to find Q point just now? If you still remember the graph that I showed to you, yeah. Where is it? Right, this one. Yeah. If you still remember the graph that I showed to you before. Okay, how to find the Q point? Let's say, let's say that this graph is given and they ask you to identify the Q point of the graph. Okay, so the Q point can always be calculated by half value of VCC. Okay, so this is the formula for you to calculate the Q point. Yeah, VCE is equals to IC VCC. Okay, half of the VCC value. So for this, the VCC value is the maximum of VCC value is 12. So half from VCC value, so it's 6. So it means that the IC current at the Q point is 40. Okay, the IC current for the Q point is 40. All right. Okay. All right, next. What is the purpose? Okay, purpose of BJT biasing, bipolar junction transistor biasing. What is the purpose for you to do the biasing? Alamak, tak nampak pula cerita mata ni. Okay. Wait. Some of the cannot be seen. Okay. Wait. Alright. Cerita mata ni. Present now a window. Okay. Oh, sorry. Okay, now, what is the purpose of BJT biasing? So the purpose of BJT biasing, there are 3 purposes here. So BJT should be biased to determine, okay, for you to determine its operating point or Q point. Okay, for you to determine the Q point. What is the Q point? Q point is the operating point for the transistor. Okay, usually the key point will represent the operating point. At that point, the transistor will operate. Okay, moderately operates. Okay, and then from the BJT biasing also, to ensure whether it is in active region, okay, to ensure that the transistor is in what region. If it is in active region, it can be used as amplifier, or if it is in a saturation region, it can be used as switch. Also, if it is in a cut-off region, it also can be used as a switch. So you want to ensure in which region the transistor in. Okay, so this is another purpose of BJT biasing. So next, another reason why BJT biasing is important. It is a good biasing circuit must have Q point at the center of the DC load line to obtain maximum symmetrical output swing. Okay, to obtain a maximum symmetrical output swing. So you want to have maximum output. Okay, so that's why you need to know the Q point. In order for you to know the Q point, you need to know the BJT biasing. You need to know the bias of the transistor for you to plot, for you to plot the output, the collector characteristic or the output characteristic for the transistor. So all of this, to plot this graph, you need to know the biasing of this transistor. Okay, so based from this graph, you can identify either the transistor, it is in active region or in a saturation region or in a cut-off region. Okay, you also can identify what is the value from what point of VCE to make the transistor in an active mode, at what point of the VCE, what value of the VCE to make the transistor in a saturation or in a cut-off region. Okay, so that you can apply this transistor based on the application that you want the transistor to work in, right? Okay, so now let's look the graphical analysis. Okay, graphical analysis. Okay. Graphical analysis, we're gonna look by using the collector characteristic or the output characteristic of the BJT biasing. Yeah, we are not using the input characteristic. We are using output characteristic, where the x-axis represent the output voltage VCE and the input and also the output currents IC. Okay. So now this is the circuit. This is the DC bias circuit. Okay. So the transistor is biased with VCC and also VBB. Okay. And to obtain values of IB, okay, from this VBB and VCC, you will get the value of IB, IC, IE, and also VCE. Okay. So from this curves, okay, from this graphically illustration graph, okay, you can determine, okay, you can identify the effect of DC bias. Okay, we're going to use this graph to identify the effect, the DC bias. Okay, so let's say at the IB here, okay, we're going to use three values of IB here. Okay, three values of IB to observe what will happen. Okay, what will happen to IC, to this IC, and to this VCE. Okay, with three different values of current at the base here. All right. So first of all, okay, the value of IB is equals to 200 milliamps. Okay, so it means that the VBB here will be regulated to produce, to make sure that the current produced at the base here is 200 milliamps. Okay, so at the 200 milliamps, okay, the value of IC can always be calculated using this beta DC formula. So the collector current, okay, using this value is calculated as 20 milliamps. Okay, using here 20 milliamps, 20 milliamps, 20 milliamps here, yeah, 20 milliamps. So it means that the graph now is at this point, yeah, the IB, the value of IB is at this point, 20 milliamps around this, yeah, at this point. It cannot be this graph and it cannot be this graph because this is too large, this is too small, and it should be around here. So we're going to select this graph, yeah. So how Q1 Okay, Q1, so VCE, what is the value of VCE? Okay, value of VCE is equals to VCC, okay, to plot Q1, yeah, to plot Q1, first of all, yeah, VCE equals to VCC minus ICRC, okay, VC, yeah, ICRC. So you will get the value of VCE now is 5.6 volts, okay, VCE. Okay, at this state, you cannot use VCE equals to half VCC. Why? Because now the the voltage of currents is variable. I mean, the voltage of currents from the base here is changing. Okay, it's changing. It is not specific voltage anymore. You can only use this value when the what the given value, the IC and also the VCC is VCE. VCE is specific. Okay, you can only use this when the value of IC is specific. But now the value of IC is not specific, right? It's not specific. It is changing here. It is changing. So if you want to calculate the value of Q1, you need to take into account also the potential drop at the VC here. So VCE now is equals to VCC minus with the potential drops from the resistor here, and you will get the value of Q point is 5.6. So at this state, okay, at this, you can mark the point of Q1 is 5.6. Okay, 5.6. This is 200 milliamps. When the IB is 200, this is the value of IB. This is the value of IB. So when IB is 200 milliamps, the value of Q1 is 5.6. Someone just joined. Okay, now let's, because now you want to plot a you want to make a DC load line. Okay, so in order for you to make a DC load line, only one Q point is not enough. So you need to take a few more points from others IB value. Okay, so let's take another value for IB. So next, IB is increase. Okay, you increase the IB to 300 milliamps. Okay, 300 milliamps. Okay, and the VBB is now regulate. You change the VBB so that the currents produced here is 300 milliamps. Okay, so when the IB is 300 milliamps, okay, 300 milliamps, you already know. You can find from IB is 300 milliamps. First of all, you need to know the IC. So IB just now is BDC is 20, right? 20. Okay, so VDC is 20. So you will get the currents of IC here, that flow here is 30 milliamps. Okay, so you will get the point for Q2 VCE here is 3.4 volts. So you can another plot here when the IB increase to 300, you will get another plot here. Okay, which is 3.4 volts. Just now is 5.6, right? Another plots here. Okay, now you already have two plots, right? So let's find another one, okay, to make a nice straight line of DC load. So now let's take the IB is 400 milliamps, microamps, sorry, 400 microamps. So 400 microamps, the value of IC around 40, right? Around 40. Okay, when 400, the value of IC is around 40. Okay, so you can calculate the value of VCE, which is also the value for Q3. You will get 1.2 volts. Okay, 1.2 volts. So 1.2 volts. 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 1 So now you already have 3 points, right? 400, 1.2 volts, 1.2, 300 just now, 3 point something, right? 3 point something, and 5.6 for 200 just now. So now you have three lines here. You can make a straight line then. Okay, so from here you can get the value for saturation value and the cutoff value. Okay. Okay, so from that you can make a DC load line. Okay, so this is the DC load line. Okay, DC load line, and from here you can get the value of saturation value and also the cutoff value. Okay, so this is how this is how you want to find or you want to create a DC load line. Okay, don't just take only 2 points. Okay, try to take as many points as you can, but if you take too much point, it will wasting your time. Okay, for calculation, usually 3 to 4 points is enough. 3 points is enough. Okay, 3 points is enough. All right, so try to take 3 points, and then from the 3 points you can connect the dots, and then you can create the DC load line. All right, and yeah, be careful. Yeah, don't take too much points. It will waste your time. But if you take too less, or a few number of points, also it is not enough. You will not get a nice straight line. Okay. Okay, next. Okay, Q point at the center of DC load line. Okay, this is as I mentioned just now. Yeah, usually Q point is placed at the center of DC load line, but there is also possibility that Q point is not located at the center or in the middle of DC load line. Okay, so it means that the transistor is not ideal. For an ideal transistor, the Q point is usually at the center of the DC load line. Okay, so let's look. Okay, what will happen if the Q point is not at the center of the DC load line? Okay, so if the Q point, okay, is driven into saturation, it means that it is located near. Okay, it's near to saturation. Yeah, it's located near to saturation. It means that the signal, yeah, the signal might be distorted at this point. Okay, at the saturation, when the transistor work at the saturation operation, the signal might be distorted. Okay, the output signal might be cut somewhere. Okay, you will not receive a very good signal then. Yeah, this is the input signal, right? The input signal. At this signal will be cut or will be missing. You will miss this signal at the output part, so you will not have a clear signal. Okay, so it means that the transistor is now at the stage of saturation. Okay, transistor is driven into saturation because the Q point is too close to saturation for the given input signal. Okay, next, when the inputs, what will happen when the Q point is too close to the cutoff? Okay, if it's too close to the cutoff, you can see when the input signal is driven too close to the cutoff, okay, the Q point also will be driven near to the cutoff. So it means that this signal, okay, this signal at the cutoff here will be distorted. Okay, you will not receive or you will not transmit. This signal will be cut. Okay, so you will not have a nice output signal as well. Okay, next, what will happen if the signal, okay, is the Q point what will happen if the input signal, okay, is too large? Okay, too large. Okay, the Q point, yeah, the Q point will be still in the middle, but you can see both at the saturation and at the cutoff. Yeah, at the cutoff output signal, the signal will be distorted. Okay, so you have to control. Okay, you have to control the value of the current. Okay, I put input signal value at the base lah, yeah? The value at the base, you have to control to make sure that the signal at the base, yeah, the signal at the base is nicely driven between the saturation and the cutoff. Okay, between the saturation and the cutoff, so that the output signal that you receive is totally clear signal. Okay, like this. Okay, totally clear signal. Okay, for here you can see here the IB maximum and the IB minimum is within the range. Okay, within the range. Okay, and then you can see at the output signal for the currents is nicely can be detected, and also the output voltage, yeah, is also nicely can be detected. It is not distorted at any point. Yeah. So this is the importance of the Q point. Yeah, Q point for the DC load line. All right. Next. Okay, let's look BJT DC load line. All right. A straight line. What is a BJT DC load line? What does a load line mean? Load line is a straight line, okay, intersecting the vertical axis, okay, vertical axis that will give you a value of currents at the collector when it is saturation, okay, saturation value, and the horizontal axis at the VCE, which is the cutoff value of the transistor. So IC saturation occurs when transistor operating in saturation region. Okay, IC occurs when the transistor is operating in the saturation region, when the IB is too large. Okay, too large. So it means that the transistor now is operating inside the saturation region. So IC, how to calculate the point of IC? IC saturation is VCC divide with RC when the VCE is 0. Okay, VCE is 0. Okay, this formula is only applicable, or you can use when the VCE is 0. It means that there's so much current. It means that the resistor, the potential drop at the resistor of the collector is too big until all the until no voltage left at the VCE. Okay, so this formula is applicable when VCE is equals to 0. Okay, you can find the value of IC saturation. So VCE off or VCE at the cutoff region occurs when the transistor operating in the cutoff region. Okay, when the transistor is operating in the cutoff region. For you to find the value of VCE, okay, is equals to VCC. Okay, VCC, the source, external source at the collector, okay, VCC minus IC RC when, okay, when the value of IC equals to 0. It means that there is no current flow in the IC. Okay, only that it will give you VCE as the value of VCE at the cutoff region. Okay, next. Okay, so this is BJT DC load line. Okay, so this is a Q point when the IB value at different Q point at different IB value, yeah, base current value. Okay, different base current value. Okay, so to make sure that the chosen Q point is useful for amplifier application, the Q point, it is best located at the center. Sorry, wrong. At the center of the DC load line. Okay, so to make sure, okay, for you to make sure that the Q point is can be used as amplifier. Okay, you have to make sure that the Q point, okay, is at the center of the DC load line. Okay, so for this point, okay, for this graph, yeah, for this Q point here, the one that you want to choose is Q4. Okay, Q4, because at the Q4 it will amplify. It is in the middle, and it will amplify. It will amplify nicely. Okay, it means that the input signal will be transmit, and at the output signal will receive clear input signal. But if you choose Q2, then it means that at the saturated region, it will distort. Okay, at this point it will distort. But if you choose Q6, okay, at the cutoff region, it will distort. Okay, so for this, if you want to choose a point, Q point to be used for amplifier, you should choose Q4 load line. All right. Okay. So at where at the Q4, okay, at Q4, the VCQ is approximately half VCC, and also at ICQ is usually half IC. All right. So this is example 3. So example 3 actually I took from the reference book that I given to you. Okay. All right. Oh, okay. Meetings. Wait, yeah. Okay, right. Sorry, I just got information of meeting. Sorry. Okay, so for example 3, determine the Q point for the circuit in the following figure and draw the DC load line. Okay, you need to draw the DC load line and find the maximum peak value of base current for linear operation, and assume that the value of beta DC is equals to 200. Okay, so first of all, for you to draw the DC load line, you need to find the value of IC, right? And for you to find the value of IC, you need to know the value of IB first. So how to find the value of IB? Okay, the value of IB is same, V equals to IR. Okay, VBB, okay, minus with the potential drops here, 0.7. Don't forget the potential drop at the VBE here. Okay, so VBB minus 0.7 and divide with the value of the resistor of RB at the base, yeah. So it will give you 198 microamps. Okay, so usually currents at the base, yeah, usually around microamps, and currents at the collector and current at the emitter usually milliamps. Okay, usually, yeah. Okay, next, once you get the value of IB, you will get the value of IC too. So the value of IC, you can use this formula. Okay, you will get where beta DC is given to you, you will get the value of IC is 39.6 milliamps. Okay, so once you get IC, you can also calculate the value of VCE, right? VCE. So VCE is equals to VCC minus with the potential drop at here. So you will get around 6.93 volts. So from here, can you plot the graph? Yes, you can plot the graph where the Q point is at IC, which is 39.6 milliampere, okay, milliamps, and at VCE it's 6.93 volts. Yeah, so this is the Q points. Okay, Q point at the specific value of IB. Okay, at the specific value of IB. Okay, so next, you already have Q point, but how you want to find? You cannot plot the graph yet, right? You need to find the value of saturation and also the cutoff. So for you to find the value of current at the saturation at the collector, current at the collector when saturation, so VCC divide by RC. Okay, VCC divide by RC. So you will get 60.6 milliamps. And from here, you also 60.6. Okay, so this is the value for ideal saturation. Okay, next, for you to get the value of cutoff, how to get the value of cutoff? Okay, to get the value of cutoff, it is 60.6 minus 39.6, you will give around 21 milliamps, which is nearer to 20. Yeah. However, IC can decrease by 39.6 milliamps before cutoff, which is IC equals to 0. Yeah, it's reached. Therefore, the limiting excursion is 21 milliamps because the Q point is closer to saturation than to cutoff. Yeah. This Q point is closer to the saturation compared to the cutoff. Yeah, so this Q point is not in the middle of this of this DC load line. Yeah, so you can see that at the given this voltage, okay, at the given at 10 voltage, where the value of IB 198 microamps, the Q point is not in the middle of the DC load line, right? So it means that this Q point is near to the saturation. So it means that signal near the input signal, okay, will be distorted at the saturation part. Okay. All right. Next. Okay. So for this, yeah, we will continue for the next class, which is the main types of BJT biasing circuit. We're gonna look at our focus on these two circuits. Okay, these two circuits will come out in your test. Okay, this is only for additional. Okay, this circuit is only for additional, but in your test, not in your test, in your exam. Okay, in your upcoming test, BJT will not included, right? So, but for your test 2 and for your final exam, okay, these two circuit will come out. Yeah, fixed base bias circuit and voltage divider bias circuit, and this circuit is just for your extra knowledge only. So to explain about this circuit will be on next class, I guess, because I think for this class to include the analysis of the circuit, we're going to be very confusing. Okay, we cannot focus anymore then. So before we end, okay, this is the example of BJT data sheets. Okay, BJT data sheets that usually that you can when you buy any transistor in the market, yeah, it will come together with the BJT data sheets. So inside this BJT data sheets, you will get the value of VCEO, yeah, collector emitter voltage, which is 40, VCB collector base voltage, all will be given to you. Okay, you can see here, right? So this is the example of the parameter for each voltage at each junction. Also, there's also power dissipation and all. So power dissipation I'll not touch today because power will not come out in your exam too. Okay, we will not focus around power calculation of power and those things. Yeah. So, but if you want to find any information about how to calculate power and those things, maybe you can refer to the reference textbook that I given to you. I've included inside your inside your e-learning website, yeah, the electronics book, which I also refer to that book. I think that book is very good. Okay, it's easy for you to understand. All right, and then also another extra information that also will be given to you. Yeah, you can see the breakdown voltage for each junctions and so DC current gain. So this is all extra knowledge that you can get from the data sheets. Yeah, okay. So any questions before we end the class? Any questions regarding the for your test? Is open to any questions? Any questions? Is the QR code is functioning? Please let me know if the QR code is not functioning. If not, then we're gonna end the class here. Good luck for your test. Yeah. Be careful with the time. Okay, the time duration for you to answer each question is fixed. Okay, so be careful that you have good internet connection. Be careful that you have all the equipments with you, all the calculators. Don't worry about the formula. Formula will be given. You need to know how to use the formula. Okay, you need to know how to use the formula. You need to be familiar with the formula. And then, also when you write, please make sure that your handwriting is clear enough. And when you take the picture, snap the picture, make sure that the picture that you take is not blurred anywhere. Yeah, because once I cannot read, I couldn't mark well your answer. Then, okay, it's quite difficult for me, right? So, and if you have any problem with the connection or Wi-Fi or something like that, or you have late access or something like that, please quickly let me know, right? So I can I can identify you, because I'm not the one who control the website for you to download the questions. There's someone else who control the website, so I need to let the lecturers who control the websites know, so that they will notice you. Right? So any questions? No. So good luck, yeah, for your exam, for your test, which is on this Thursday. If anything, you can just always message and contact me. All right. So, all right. So, Assalamualaikum. Thank you so much.
Thank you, Sensei.